Hello and welcome to our second lecture on clustering analysis. In the first lecture we introduced the idea of clustering, differentiated it from say classification and other supervised learning techniques, and we explained what clustering is, how it's useful, where it can be used, and also gave you a brief overview of the different types of clustering and the different types of clusters. In today's lecture we're going to introduce two very popular clustering techniques. The first is the K-means clustering, and the second is called the hierarchical clustering. While both these techniques are fairly old, they still enjoy immense popularity in terms of being actually used. The first one, the K-means clustering, and is this choice of K-means and hierarchical you should find to be also fitting the first dichotomy that we used when we talked about clustering approaches, which is partitioning based approaches and hierarchical approaches. So the K-means clustering is essentially the partitioning based approach, and what we'll do is we'll dive into the algorithm, right? So we've already mentioned that it's a partitioning based approach. So it's one where you partition the entire data set into K clusters essentially, and it's also very useful to think of the K-means as a prototype based approach, where that's also something that we discussed in terms of how clusters are formed. And the prototype based approach is one where there's like this representative for each cluster, and you use these representatives in some fashion to express what a cluster is and to also form the clusters. So it's essentially this prototype based approach where you create K clusters, and it's also noteworthy that it's an iterative procedure. So even right at the end of the first iteration you already have K clusters, and they might not be good clusters because it's just the first iteration. And then, like most optimization procedures, like steepest descent or any of these other iterative procedures, you'll find that over time you're just refining a solution, and at some point it doesn't make sense to refine anymore. Your clusters are not changing. Essentially, your prototypes are not changing either location or who they are, and so you stop at some point. Okay, this procedure is ideal when all variables are quantitative. By that, what we really mean is that you should be able to take each data point, and you might have some other data point or some other location, and here location is defined across the multiple attributes associated with this data point, right? So a data point, again, the conception you should have in your mind is these rows, and you're basically grouping data points. That's your job, and each data point is described by some attributes, which are these columns in a table, and each column means something, right? So with the K-means procedure, what you're doing is you want to say that you want to take this conception and you want to actually be able to compute distances between 2 points across these dimensions, which means the attributes themselves need to be quantitative. This in a lot of ways should remind you of this K nearest neighbors examples that we took up, especially in the case of K nearest neighbors regression, right, where each of these dimensions in each data point is a continuous quantitative variable. Okay, and once you do that, you should just be able to compute distances. Typically, whenever it comes to computing distances, we've always used Euclidean distance. You could also use other measures of distance, and you would actually it would still be a K-means procedure with a different approach. So common ones are Manhattan distance, Euclidean distance, and so on. Okay, so how does it really work? So let's just go through the algorithm in some sense, and then we'll see a graphical representation of it. The idea is to initialize some cluster centers K. So what do you mean by initialize cluster centers? What we mean is essentially think of this, and it's easy to think of it in a graphical sense, or you can think of it in a mathematical sense, but the idea is that each data point can be expressed in terms of an x-axis, y-axis, z-axis, w-axis, so on and so forth, depending on the number of attributes there are, right, that represent each data point. Now, while each data point is represented based on these different attributes, you can create a cluster center also on these attributes. And often it really makes sense to put cluster centers where you think the clusters are going to be formed, but you'll see how even if you don't do that perfectly, sometimes the k-means clustering will adjust for it. But the most important thing to take away from this is that the k-means clustering algorithm therefore could be sensitive to where you place the cluster centers. If you don't place them in sometimes the right places, you could get to a solution which is not necessarily a good solution. Okay, so the idea is that you initialize some cluster centers. So specifically, you'll initialize k cluster centers. So you'll because it's k-means clustering. So k is usually a number between 2 and maybe 10 or 20, depending on the higher limit is a little more vague. Most problems you're looking at between 2 to 6 or 7 clusters at the most. But there are contexts where your data set is really large, or what you intend to do with the clustering is such that you don't mind having more clusters. Okay, so the algorithm initially you drop in k cluster centers, and then what you do is you take each data point and you figure out which of these cluster centers is closest to the data point, and then you assign that data point to the closest cluster center. Okay, and so essentially it's like if you kind of gave names. So just to give you some insight, this is where we are. We're in the second bullet point. So what we're doing is we're basically saying if you wanted to give those k cluster centers name as cluster 1, cluster 2, cluster 3, then what we would do is we would go to each data point and say, hey, which cluster center is closest to you, and then I'm going to assign you to that cluster center. Okay. Now, once all of these points have been assigned, what we're going to do is we're going to recompute the cluster center to be essentially the centroid of this assignment of data points derived from step 2. So what we're going to do is essentially in step 2 what you did is you assigned a whole bunch of data points to different clusters, right? So what we'll do is we'll then, for instance, take all the data points that were assigned to cluster 1, to centroid 1, essentially to the cluster center 1, and we gave them all the labels that, hey, you're assigned the data point X, you're assigned to cluster center 1, data point Y, you're assigned to cluster center 1. So all of them that were assigned to cluster center 1, we'll take those data points and compute the centroid of those data points. Centroid essentially is in many senses like an average, right? It's again, it depends on exactly what measure of distance you choose, but if you were choosing Euclidean distance, the centroid is essentially like the average, and we say it's the average of these data points, but it's called the centroid because it's the average across all those dimensions, and the number of dimensions are the number of attributes, right? So across those dimensions, what's the center? So once all these points have been assigned, you kind of compute a new cluster center based on the centroid, and it's essentially like you forget the old cluster center, and now this new cluster center is your cluster center. And you do this for each assignment, right? If 10 data points were assigned to cluster center 1, then you do this step for cluster center 1 data points, and then you go to the next 15 data points that were perhaps assigned to cluster center 2. For these 15 data points, find out the new centroid and call that the new cluster center. So you've got a new k set of cluster centers. What do you do next? You iterate. For these new k cluster centers, you go to each data point, and it's almost like you forgot which cluster center that data point belonged to. Because remember, that data point was assigned to, say, cluster center 1 or 2 based on the old centroid, right? Based on the old cluster center. Now, because your cluster centers have moved based on the centroid, you now assign them all over again. And once you've done the assignment all over again, you find the centroid. Once you find the centroid, you do the assignment. That's how it's an iterative process. So essentially, you're repeating these steps 2 and 3 until the centroid is not moving any further. Or in some cases, you might say the centroid is moving by an amount small enough that is within your tolerance. So this was fairly abstract in terms of bullet points. So let's actually take a graphical look at this. We've taken an ultra simplistic example where there are only two attributes. So let's say attribute is x1, x2. Always remember that with clustering, which is unsupervised learning, there's no y, there is no output variable. What we're doing is trying to group the data, and here is the data. The data are these blue squares, and you're trying to group these blue squares. Now, a fairly naive look at this can kind of make it obvious that perhaps this is one cluster and this is one cluster. Okay, so the blue dots are actually the data points. Now that's to the naked eye, and the things to remember are that if for instance there were more dimensions, there were more attributes beyond x1 and x2, it would be harder to show you this visually, right? So at that point the math kind of takes over. In three dimensions I can show you x1, x2, x3, but then after that what do I do if you have more attributes? Okay. So the squares are essentially the data points, and let's say the k-means clustering algorithm started with two centroids. Here obviously that means k is equal to 2. So you've initialized two centroids, and these like I said, the algorithm itself to some extent could be sensitive to how you initialize a centroid. So there is a right way and a wrong way. Ideal would be if you could actually plant the centroids right in the middle of the clusters, but often we don't know that yet. That's why we are doing a clustering. Okay, so what's the first step in a clustering algorithm? The first step is to take each data point and see which cluster center is closest, right? So let's say we take this is data point 1. Clearly the yellow cluster center is closest, and at least so for a set of data points, this yellow is closest. Obviously for another set it looks like the green is closest. So each data point basically gets an assignment. It either gets assigned a yellow color or a green color, and that's essentially what I've done. These diagrams are more conceptual, not to scale, so I've kind of eyeballed it and said it looks like these 4 data points are close to the yellow, that these 4 are close to the green. So that's how they've been assigned. What's the next step? The next step is, given this assignment, the new cluster center for the yellow data points is the centroid of the yellow, right? So what is the centroid of the yellow? So you can think of it as essentially the average of the yellow, and average obviously needs to be on this axis as well as it needs to be on this axis, right? So where would you centrally place yellow so that it's minimizing the squared deviation, which is Euclidean distance, to each data point? That's the definition of centroid. And so we move the yellow circle to be the new centroid, and it's probably going to come somewhere here. And the green circle, now the green circle has a little bit of a problem, right? It just can't move to the center of this space out here because it obviously has an assignment. So this is going to bias where the green moves, so perhaps it'll move somewhere here. And that's what I do in the next step. I actually move the yellow and the green. But once I move it, right, it's like the assignments are completely lost. You've forgotten the assignments, because remember, the assignments were made with the old centroids, right? Now with the new centroids, you just have new cluster centers and no assignment. You redo the process. Okay, when you redo the process, you see now which blue dots are closest to the yellow and which ones are closest to the green, and we repeat the process. And as you can see, we've already gotten a pretty good results out here with the yellow and green classification, which matched our intuition about what the two clusters on this graph was. Clearly in the next step, for instance, this green will move right into this cluster center. The assignments themselves won't change too much. Perhaps the yellow will move a little bit out here, but essentially after maybe 1 or 2 more steps, the centroids will stop moving. Your assignments would probably be the same, so even if you'd stopped 1 or 2 stages earlier, you would have gotten the clusters that you were interested in. Okay, so I hope this gives you some idea of what the k-means algorithm is. Now, another very popular prototype-based approach, which can work and go beyond, k-means in some sense, which can go beyond quantitative attributes. Because remember, for this whole algorithm to work, you had to be able to compute distances, and it made sense that your attributes x1 and x2 were quantitative and continuous, right? x1 and x2, there's a little, there's medium, there's more, and there's this. It's a continuous quantitative variable. Now, many times you don't have that, right? So a very useful alternative is K-medoids in that case. Now, K-medoids allows you to go beyond quantitative variables, and so when you have categorical, or rather more importantly nominal variables, where the variable is are things like male, female, and the attribute is like male, female, or things like that, you can use K-medoids. But more importantly, right, K-medoids allows you to go beyond attributes altogether, right, where x1 and x2 was an attribute, to a point where all you need is some dissimilarity matrix. What do you mean by a dissimilarity matrix? What I mean is, you have all these data points, right? Let's start calling them 1, 2, 3, 4, right? Now, with k-means, the distance between, and I'm going to give you the same data points in the columns, right? Now, with k-means, I can compute the distance between data point 1 and data point 2 through some form of Euclidean distance and marker value x, right? But what if, so the whole process of using Euclidean distance required that I go into each attribute, look at how different it is, and then compute that, right? Squared distance and take the square root. But what if I did not have that process, right? What if I had a process where I gave you just the differences between each data point? So I had something like a dissimilarity matrix, right? So when I have a dissimilarity matrix that I'm giving you, and you can get the dissimilarity matrix through completely different ways, right? It can be a user survey, or it can be something extremely subjective where you say, I feel like 1 and 2 are different by this much, and I can tell you how different 1 and 2 are, and I can tell you how different 1 and 3 are, and I can tell you how different 1 and 4 are, and so on. But I can't really break it down into 5 different attributes and give it to you that way, right? So people do this a lot of times in social science research, where there's some kind of a questionnaire that's given to people to tell, so please tell me how different these two are. And people are able to say that, but they're not able to break it down into a set of quantitative variables and say how different they are on each of those dimensions. So K-medoids is very useful when you don't have these attributes, but you just have this dissimilarity matrix of how each data point is different from every other data point. Okay, so you'll essentially just need some kind of a leading diagonal of data. So the data is either on this side or data is either on that side, because 1 is different from 2 the same amount that 2 is different from 1. There's no difference between those two. Okay, so in cases like that, K-medoids primarily winds up not having this arbitrary cluster center, because you really can't any longer compute things like centroids, right? There is no centroid, there are no dimensions on which. So what winds up happening is you'll nominate a data point to be that prototype, and you'll use the same core concept of k-means, in that you'll first nominate a data point, and then you'll do an assignment where each data point chooses between the nominated data points, and once you have one assignment, you find the new nominated medoid that should become the representative data point. It's kind of like the idea of being a cluster center. Okay. Now, while this works, an important point is the computational intensity associated with such an approach. Now, when you had 10 or 20 data points which had an assignment, right? So let's take all these data points, right? The computing the average through sum of squares just was essentially like using the sum of squares minimization was essentially just computing an average of these points across each of these dimensions, right? Now you don't have something like that with K-medoids. Once you have an assignment, to choose which for this assignment what should be the prototype requires you to see the dissimilarity between each data point to each other. So the number of computations that you need to assess really grows. And so K-medoids is often seen as a very computationally intensive approach. Okay, so this should give you some idea about K-means and K-medoids. The next approach that we're going to talk about is hierarchical clustering. With hierarchical clustering, you don't really wind up fixing a fixed number of clusters, and essentially the approach itself starts with either one very large cluster and breaks it down step by step. So the first one, one way of doing it is called the divisive way, which is you have one large cluster which has all the data points in it, and then after that I break it into two clusters, and then after that I break it into three clusters. So I look at the two clusters that were broken up and I choose how to break them down further. And that's called the divisive approach. You also have the other approach, which is agglomerative, and definitely the more popular approach, which is bottom up, where each data point becomes a cluster. So you have all these, so you have the number of actual clusters you have is equal to the number of data points, because each data point is a cluster. And then after that, you choose the two closest clusters and merge them together. And we'll talk about how closest is defined. So you choose the two closest clusters and merge them together. So at the end of the first step, you're essentially having, if you had n data points, you're having n minus 1 data points at the end of one step. And after that, in the next step, you'll have n minus 2. Because now you'll have n minus 1 clusters, where all of them except one have one data point, and one cluster has two data points, but you're just treating them as clusters. And you're saying, now out of these n minus 1, which are the two closest clusters that I can merge? And that is seen as a bottom-up approach. Now, because of how we do this, essentially you're going to have nested clusters, right? Think of the divisive approach. If you created two clusters, right? Now, when you go to create three clusters in this divisive approach, you're going to take either cluster 1 or cluster 2 and break it further. And the other is going to be the same. So one breakup could be that cluster 1 stays the same and cluster 2 gets broken up into two pieces, right? So in many ways, the clusters that you're creating are nested within one another. You can think of them as parent and daughter. And the same approach goes for the agglomerative, right? Where you started with many individual clusters and you're choosing to group them. It's never like you're breaking one grouping. You're rethinking an action that you did in the previous step. You're never, in some sense, going back in time and recorrecting a decision to either group clusters or to break clusters. And so in some sense you can think of this also as a partly greedy approach. Okay. Now we spoke about how we're going to take with especially the agglomerative, which is what we'll focus on in the rest of the lecture, because it's the more popular one, and for a very specific reason that we'll talk about. You need to take, in the first step, for instance, you have n data points and n clusters. You need to take the two closest clusters and merge them. How are you defining closest clusters? And the way you would kind of define them is through some measure of dissimilarity between the clusters. An example is, for instance, that there are many definitions of dissimilarity. The three of them that are listed here really talk about it more in terms of come more from graph theory. And the first one is called single linkage. And the idea behind single linkage as a means of talking about dissimilarity is that it's essentially, when you take two clusters, you take the minimum distance between two data points that can be in the two clusters. So don't think of it as much in terms of the first step, right? Within each cluster there's one data point. So it's not a very interesting case. Now think of a case where you've got this cluster and you've got three data points. That's what I've shown here. Let me give you a concrete example. So here is one cluster and there are three data points within this cluster. Okay, here is another cluster and here are let's say 4 data points. 5 data points. Okay. Single linkage basically takes each combination and sees which combination is minimum. So in this case, probably this would be minimum, and so it's for that reason it's actually called min as a definition of dissimilarity. Complete linkage, in contrast, takes the maximum. It is which of these combinations I need to take one from cluster A and I need to take one from cluster B. Which combination of points can I take such that I get the maximum distance? And I'm probably guessing that this connection that I just drew would have the maximum distance. There's group average, which basically takes every combination of every point to every other point and takes the overall average. Now, in addition to that, you also have some approaches that try the more prototype-based ways. And there you would, for each cluster, try to create a centroid, and from that centroid you'd look at the distance from one centroid to the other, and so on. And there are some other approaches. There's the Wards method and so on, where you're again trying to take some kind of a more prototype-based approach to define the dissimilarity. Okay, but essentially hierarchical clustering it's all of these still come under the broad umbrella of hierarchical clustering. Okay, so there are two important things in connection with the hierarchical clustering. As you can see, because it's doing this nested clustering where you start from with agglomerative, you start with each data point being a cluster and you keep merging them till you have this one mega cluster of all the data points. And in the other way around, with this divisive, you start with this one mega cluster with all the data points and keep breaking it till each data point is its own cluster. So therefore, you've not really committed to creating clusters of a specific size k, right? And you can therefore take you can kind of look at the results overall and make a decision in terms of what your size should be. One important property that we see with all agglomerative, when in some divisive methods, is that they possess this property called monotonicity. And the idea here is that the dissimilarity between merged clusters is, so there's some way of measuring the dissimilarity of a cluster, right? So that the dissimilarity between merged clusters is monotonically increasing with the level of merger, and that should be fairly intuitive, right? When you think of the dissimilarity of a cluster which has just one data point, there is no dissimilarity, right? It's only when you have two data points that you can say these two data points are different by this much. So with agglomerative clustering, in some sense, the more number of data points that you have into a cluster, the greater the amount of dissimilarity there. And that monotonicity is strictly maintained with agglomerative clustering. So a very useful way of representing it, therefore, especially when you have this monotonicity, you can graphically represent agglomerative clustering through something called a dendrogram. And what is shown in this slide is the dendrogram, and it's essentially this binary tree which is plotted so that the height of each node is proportional to the value of the dissimilarity between its daughters. So what is a node here? Essentially, you can think of each partition as being a node, right? And the height of this node, right? So let's take something very simple. The height of this node has to do with this height, right? Has to do with the degree of dissimilarity between B and C. So you're forcing B and C to be in a cluster right now. That's what you're doing by this this part of the graph. That's what it's doing, right? This height has to do with the dissimilarity of B and C, which is why, for instance, perhaps D and E was merged first. So with agglomerative clustering, think that you're going bottom up and you're sequentially making decisions. And so if you chose to put D and E together first, that means D and E would have been less dissimilar to each other than B and C, and that's why D and E was done first, and then B and C was separately done perhaps later. Now, the really good thing about this dendrogram is that now you have a full picture. You can now choose to say, I'm interested in the situation where there are 3 clusters, and you can essentially draw this horizontal line, and you have the 3 clusters. Cluster 1 is just data point A, cluster 2 is data point B and C, cluster 3 is data points D, E, F and G. Right? You basically see what goes into each of these limbs, and that's essentially your cluster. So at any level, when you draw a horizontal line, the number of vertical lines it cuts across is the number of clusters that you have in your thing. So obviously, if you had a line out here and you drew it here, there's just one cluster. Out here there are 2 clusters, and so on. Okay, so this should hopefully give you some idea about the 2 very popular algorithms, K-means clustering and hierarchical clustering, and in hierarchical more specifically agglomerative. Thank you.